ANSYS 19.2, and we use Workbench as our integrating software. So Workbench is where we pull in the design model, the meshing, and the Fluent portion of it where we solve for fluid flow. So that's what we use.
It's Workbench, right?
Yeah. So we solve our fluid flow using Fluent. So if you just click on that, it'll open up a workbook. You can name it whatever you want, and then you start building your geometry. We mainly deal with 2D. So I changed the analysis type to 2D and then start working on my geometry. We use Design Modeler. So if you right click, you get options. You can have space claim, but we use Design Modeler for our geometry.
So you are remotely accessing the big workstation?
Yeah.
Okay.
So yeah, I usually work with in the XY space. So that's what I'll be doing today. And that shows me the X and the Y axis. And I can start sketching from here. As Dr. Camacho was mentioning, we basically model everything in a rectangular zone. So my workspace is basically going to be a rectangle with inlet, nozzle inlet, and outlet flow, and different boundary conditions. So it starts off with a rectangle. Oh, before that, sorry, I forgot. Change units to centimeter. And then, yeah, and then now I can start assigning dimensions to these by going to dimensions, and then just general, you should be able to get your dimensions. And I can assign my dimensions. So the way we have it in this setup is this is an axisymmetric profile, so we are only showing half of it. The horizontal line is our axis. So basically here the flame is tilted 90 degrees. So the horizontal line here is our axis, and this is our stagnation wall. So
is there a reason why you do that? Or can you just have the Y be your axis? Like why do you turn it 90 degrees? Is there a reason, or just for your specific project it makes sense?
Camacho started doing it and I just continued it.
I think
you've done both. I've seen.
Oh yeah, we've done both. And I think in the fluid mechanics, you can turn gravity on and off, or you can specify where gravity goes.
Yeah.
So it doesn't matter so
it wouldn't matter, really?
It does if you want, like for maybe this chamber, it would, but not for this flame, because there's no buoyancy effect in anywhere. But a lot of other flow problems would have some buoyancy effect. And
right, but in the case that there was, you could specify where.
I think so. In Fluent, you can specify. I think the default is Y.
Mm-hmm. Yeah,
negative Y. I think the default is negative Y. Yeah.
Okay, I just curious.
Yeah.
So I set mine up the other way. So just asking.
So we usually work with a separation distance of about 1 inch between the nozzle and the stagnation plate. So our horizontal distance here would be 2.54 centimeters. And vertical, usually I use a 7 centimeter domain, 7 by 2.54 centimeter domain, just because I'm kind of giving it room for the flame to look prettier. So and then now we can start making our nozzle inlets and orifice outlets and all of those things by making splits on our walls or lines right now. So I want my, considering this is my nozzle, this is going to be my nozzle inlet. Then I have my sheath flow inlet, which is the way our burner is. We have the nozzle, and then we have a concentric sheath flow. So that's the sheath flow inlet where the sheath flow is going to come in. And then we have the orifice on the other side for our sampling probe.
See it now.
Yeah, so let me see if I can find this.
Okay, so you made a slit.
I made a slit for the orifice and the nozzle inlet and nozzle outlet.
Do you see how she did that, Elena?
Yeah, I saw that. Thank you.
So
yeah, I saw that in a video one time, and it was perfect.
It's easy, yeah. It's way easier than I would have thought it is. Yeah, and now I can just mention the dimensions of all my geometry. So my nozzle diameter is 1 inch. So this is, because it's axisymmetric, it's going to be 0.5. And then my slit is 0.04.
And so that's the particular burner we have. And then Elena, Shruti has before did a concentric flow where there was 2 slits. And they're both issuing different flows.
Yeah.
And I think, Elena, that's what you might need to do, because it seems that this 120 liters per minute of nitrogen surrounding the spray flame probably has an effect on the flow field.
Oh, yeah, I had planned on doing that.
Right now.
What's that? Say that again, Shruti.
This is a concentric flow too.
Oh, so you are doing that? Okay.
I did do the sheath flow.
Okay.
Yeah. And then I just create a surface out of it so that we can start meshing the surface. So you go to concept, surface from sketches, and then click on any of the lines. And if you hit apply, it's going to select all of them and you can generate a surface out of it. So, and if you save it, I'll ask you to save the project. Now you can start working on it. The next step is to mesh it. If you click on mesh, it imports the geometry in here, and now you can mesh this surface. So we do, in our, somehow we've always done a rough mesh here and then refined the mesh when we go to the fluent portion of Workbench. So right now I'm just going to do a rough mesh here, first for all the edges and then to the face. So I select edge, which is here. It took me forever to find it. So selection for edge. And
oh yeah, I remember that now.
Yeah, I can go click on any edge and insert and sizing. We just do the default sizing that comes with it. You can also refine it how much ever you want, but we do the default here and then do the fine meshing in ANSYS, in Fluent. So I do that to every surface.
Wait, so you press, when you do that sizing button, it makes a mesh?
It doesn't make a mesh. I haven't generated the mesh yet. It generates elements right now.
On the edge?
On the edges.
Oh, okay.
And then when you actually generate the mesh, it'll do the meshing. it'll
Okay.
mesh.
And then at this point, do you define an axis there? I mean, it doesn't know that there's an axis?
No, I do
Okay.
that in Fluent.
Okay.
I do label it here, but eventually it gets defined as a condition in
Yeah,
Fluent.
it's good to label it so that you know which one is
Yeah.
which.
And then I go to face meshing and select the face, insert, and I just mesh the face. And if I can either do generate mesh or just here generate mesh, and it'll generate a rough mesh.
Okay.
And now I'm going to go label each one of them so that I know what I'm referring to when I import it to Fluent. So create name selection. So that's my nozzle inlet.
Each edge that you defined.
Each edge.
And these become faces in the flow simulation.
Nozzle sheath. Call it nozzle wall, but my boundary condition is not a wall.
Okay. Oh, yeah.
Output. ANSYS. That's an ANSYS. And with the new name selections, I'm going to update the mesh so that it can get imported into Fluent. Yeah. So if it actually, everything goes well, you get a message saying the mesh translation to Fluent was successful, meaning that now you can access it in Fluent.
Okay.
And then now we head to Fluent. That is the setup portion of it where we define all our boundary conditions and start our calculation. So we run it in parallel here, double precision. And the machine that I'm using, we can have up to 40 parallel processors. So
that's a nice workstation. Have you tried that, Elena, the parallel computing on that part?
Yeah, that's on this project.
Yeah.
Well, no, I haven't.
I think
I
we have
haven't
to
even made
look.
it to the setup.
Yeah.
But that's how I do it at work.
Oh, okay.
It's parallel computing.
So you know how to find how many processors or how many we can have on there?
Yep.
Yeah, I think it's like 8 or something on this one.
on Elena's, yeah, I think 8.
Probably.
Elena's is 8, yeah.
On Mixcodal, it's like 40 as well.
So that it's faster because of no GUI.
Yeah. Might even be faster processors.
Yeah. Okay, so it looks like it's been translated. Before we do anything units, change it to CGS because that's what we typically use. And we've already defined it as an axisymmetric profile. So that, and now we can start putting in our boundary conditions and models. So we don't do any multi-phase flow here. So I'm leaving that turned off. We do solve the energy equation for our case. For Elena's case, you won't be if you're not going to solve for combustion gases.
Yeah, we would input the temperature field.
So no energy equation. Viscous, we leave it as laminar.
But this is where Elena might use one of these turbulent models.
Yes. Yeah. And then we don't use radiation, no heat exchanger, and species. So this is where we get stuck when we try to download the USC MEC2.
Okay.
But so basically what you do is you do an import and then you select your mechanism files, which is your kinetic mechanism, the thermodynamic mechanism input file, and the transport input file. So you do that, you hit import, and it should work. Between USC MEC2 and the ANSYS 19.2, we've had issues. So I have a pre-built one in 18, which I kind of, that's my base point to start off, and then I edit that and work from there. And it works well when I do that. When I translate the 18 to the 19, that it works well. And I haven't been able to figure out why.
So is this for importing? I'm not sure what this is for. Just to import the
combustion mechanism, like for in combustion class, you use USC MEC2 and Chemkin to run your flames. So
right.
Yeah.
So for my case, I wouldn't need this though, right?
Right.
You will need some kind of
you don't go to
no, you will need the mechanism to input the species fraction.
I think
you can't do it some other way without
this is importing from outside. I think there's built-in ones that are easier.
I think you should be able to specify a mixture.
I mean, I don't find it here. I thought there was, because I've seen it in Chemkin.
I can look. It's not a big deal.
This has only H2O and water, because Chemkin has a bunch. I don't find any here.
I think in materials.
Yeah, materials. It's materials.
I was able to select several materials there. I don't know how to apply. I mean, I haven't gotten too far into this, but I can look.
Oh, so you input go to the Fluent database. Okay.
Yeah, I mean, that's where I was looking.
Yeah, and then there's actually fuel, like methane air mixtures.
So you're going to use methane air mixture?
Yeah.
Okay.
Methane air two-step. I think that's for even combustion. Yeah, some of the videos that I've seen use these options for
flames. I can look later on my own time. I don't want to.
Oh, it did work. So yeah, and then once we have done the species transport, you can start assigning your boundary conditions. So here you can tell what your boundary represents. So the axis, because I've labeled it, I know what it is. So axis is axis. And then your nozzle inlet. So when we're defining a boundary condition, we define the nozzle inlet as a velocity inlet profile, and we provide it with the inlet velocity of the mixture gas and the species constant, rather the mass fractions of the mixture. So ANSYS prefers it in mass fraction versus mole fraction. So unless you actually click on the button which says mole fraction, working with mass fraction is just easier with ANSYS. So yeah. And we provide the temperature, velocity inlet, and species concentration. So I'm selecting velocity inlet. And that would show me say I want my velocity to be 430 centimeters per second. My inlet temperature is 300, and yeah, see, it did not input inlet, and I thought it would come up here. It didn't come up there. Oh. Yeah, here, if you do have your mechanism imported, you will have the species that you want, and you can define what their mass fractions or mole fractions are. So
even though you clicked on methane, it won't, there's no.
I did methane add, I imported it here. Maybe there's something else that I need to do.
Yeah, it's okay. Don't worry about that because I'm the only one who's gonna have to use that, so I can look that up. I'm sure I can find it. Don't worry.
Okay. Yeah, and then similarly for the nozzle sheath, it's a velocity inlet. You define the concentration, which in my case, I think even in Elena's case, it would just be nitrogen flowing. The velocity, the temperature, and the species. Then nozzle wall is the space right next to the burner. So I usually do it as a pressure outlet because it's not a wall. So you still can have flow going out that way.
Because in your case, it's open, right?
Yeah. Yeah, right next to the, so in your case, right next to the nozzle, you have wall. You have a defined wall.
Right, exactly. So in my case, it would be an actual wall.
It's just a standing burner. So there is all the open
Right,
space.
it's open. Yeah. Got it.
So I do it as a pressure outlet. And I leave it at default because I don't know what the pressure is. So I don't define any boundary condition. And then this is where the orifice inlet, I do a velocity inlet for that. And I did a negative velocity. I didn't know what the species are, but I just did a negative thing I got. I don't remember the number I got, but yeah, and it worked. So
I can see why
that one you don't need to specify the species because it's like whatever the flow, whatever it is here, it's leaving out.
Yeah, I didn't specify the species.
Got it.
And then the side outlet is the sides of the flame. So that's again going to be a pressure outlet. And
I can see why that doesn't make physical sense.
Why not?
Because the velocity going from the nozzle to the plate is positive, and then going into the orifice away is negative.
Yeah, but wouldn't that just mean that there is suction there?
Yeah, but
what we're trying to recreate
in Cartesian coordinates, it's still going the same direction.
I don't think so.
If the
I get what you're saying, yeah.
Yeah, the velocity profile at the center line gives you 100 centimeters per second or something like that. But then all of a sudden, when it keeps on going in the same direction and enters that boundary, it turns into a negative value.
So your reference changes at that point.
Yeah, I guess it would be a reference change.
Yeah, I think that's what it is. Like when at the boundary, then it's like negative, which means it's like exiting it, not entering it.
Yeah, that's kind of weird, but I guess it works.
Yeah, I don't think it's like coordinate based.
The numbers look okay, or they make sense, but it calculated it, so.
Yeah.
And then the wall is just a wall, and we define the temperature at the wall. So you can select temperature and define the temperature of the wall. And then after this, we go ahead and refine our mesh. So for that, you have this option saying adapt, mark and adapt cells. So we refine the mesh by regions and not volumes or boundaries. So I know I have this 2.74 centimeter by a 7 centimeter rectangle, but I don't want it to be refined everywhere. I want it to only to be more refined in my flow region. So now I can select where I want it more refined than the others. So I want it refined everywhere in the x-axis. So to the max. And Y, I don't need it to go all the way to 7 centimeters. I can stop it at 5 centimeters. And I hit adapt. And yes, do I want to change the mesh? Yes. And it'll tell me how many cells it started off with and how many it ended with. And I can also see that in my, so you can see that it's adapted and you have more cells. Then that region has just been divided into more number of cells.
That's cool.
Yeah, and I do.
And can you do that for like, say, 2 different regions?
Yeah.
You like do multiple of the region adaptation? Okay, cool.
You can do that. So I can even like concentrate it more here finally. And I can,
okay. I see. You can do as many. Yeah. Okay.
So, and you can define different shapes too. If I want a circle, I can do a circle. If I want a cylinder. So I just continue to do this until I get the number of cells that I want in that region or however refined I want it in that region. So yeah, we usually go up to about 40,000 cells because anything beyond that, I've seen that simulations get really slow. And we don't see that much improvement in the solution. So, and then now because we're trying to run a combustion simulation, we need to ignite the flame. So we have the inlet fuel air mixture coming in. We also need to ignite it. So we initialize conditions for that. So to do that, we need to kind of initialize, it's not boundary conditions, initialize conditions within this region where to tell me what the profiles look like. What does my oxygen profile look through the flame, or
initial guess?
Yeah, and it's an initial guess. So so I'm going to mark the regions for that so that I can specify the initial guesses in different regions. So in our fuel, we have the initial fuel inlet, mixture inlet region where we have no combustion that happens and it's just a mixture mixing and flowing across. And then we have the flame zone, and then we have the post flame zone. So I'm going to define 4 regions because we also have the sheet flow on the side. So so I do the same thing. So from my OpDiff, so we initially run these flames in OpDiff to know what our initial guesses are. So I know from that, I know what my flame position is. So for the flame that we are currently running, our flame position is at about 1.5 centimeters. And because our inlet nozzle, gas nozzle is 0.5, so only that region, the nozzle region up until 1.5 liters, I'm going to mark it saying that's my gas inlet region. And then I'm going to do my sheet inlet region, which goes from 0.5 to 0.7 in the Y space. The X space still stays the same. And then mark that. And then is my flame zone, which is it's a fairly thin zone, 1.5 to say 1.6. And that goes from axis to, I usually do 1.2 centimeters. And I mark that. And then the post flame region goes from 1.6 to say, till the stagnation surface, and mark that. So basically now we have 4 regions. We have the gas inlet region. Right above that, we have the sheath flow inlet region, and then we have the flame zone and the post-flame zone. So, and they're all marked. You'll be able to see them in, so you can see 4 regions here marked with their respective geometries. And then we can start the initialization process. It's in solution, and if you go to under solution, you can go initialization and then hit initialize. It says hybrid initialization is done, so that they do like a first pass of the solution, and then you can start patching these zones where you want to define what your conditions are. So in my first zone, which is the gas inlet zone, I can define what my mixture fraction is. Sorry, not my mixture fraction, what my mass fractions of each of my species are, what my temperature is, what my velocity is. Those are the typical things that we know. Then similarly for sheath, we know what the temperature of the incoming gases are, we know what the concentration is, we know what the velocity is. So those are the typical things we input in those. Then if you go to the flame zone, from our obdiff calculation, we know what the flame temperature is. And we can give an initial guess to some radicals like hydrogen, oxygen, hydroxyl ions, and we also do argon, which is a major species for us. So some of those major species, we give an initial guess. And then finally, in our post-flame zone, it's more of CO, CO2, water, again, argon. So those kind of major species. Basically, we define some of the majors, initialize some of the major species in this patch. So you do that for each zone, and then you're kind of ready to you're ready to run it. So now what you can do is you can start off your simulation. Your solution monitors. So in all our calculations, we monitor it. The convergence is based on whether it reaches the residual criteria. So whether the difference between the two solutions is less than a certain number. So that's how we define. And that can be defined here. If you don't want it to be based on oxygen, you can say, okay, I don't want it to be based on oxygen. You can select your convergence criteria here. And then you also wanted to save your solution regularly so that you don't lose it. So you can go to calculation activities, auto solutions, and say that, okay, every 50 iterations, I wanted to save it automatically so that if it crashes, I have a backup. And then while it's running, you also want to look at how the simulation looks. So you can say that every 5 iterations, I want to see how the residuals look. Or if you want something else, you can go make that graph here. You want to look at the temperature profile every 5 iterations. You want that updated. So, and I'll update it every 5 iterations. So, yeah. So every 5 iterations, I'll update it. And then you're ready to run. You can say how many ever number of iterations you wanted to run, and it'll start running. That was it.
Awesome.
Yeah.
Thank you.
I think Alvin also made a video of me doing this entire thing. I don't know if he ever gave that to you.
Can we make you do it again?
Maybe.
No, I think there's an option in ANSYS where you can record what you're doing. Or I made it, I recorded it, I was doing it because he wanted it for his reference.
Oh, yeah, I remember that.
Yeah, I remember cribbing, so that wasn't coming out properly. So, yeah.
Okay.
I'll ask him, maybe.
Yeah.
For it, but it's awesome. This is like very helpful. So.
Okay.
Good stuff.
I can show you one of our profiles.
Yeah, that'll be awesome.
Mm-hmm.
No, I don't want to change. Okay. So this is what we just what I extracted today.
Okay.
Oh, it did load it. Okay. Yeah, while this loads, I did look at I looked at about 50 photos between no MMT and 100 ppm MMT.
Okay.
And they're fairly consistent. So I got a 1.54 with a standard deviation of 0.008 or 0.08, one of those two.
What for both cases or each case?
This was for the no MMT case.
Okay.
And then with MMT, I got 1.5 something. It was still in the 1.5 range.
Okay.
So
yeah, that's
calculating it for the entire data set and then getting the error bars.
Interesting.
And maybe what we can do is, as you said, average how many of our images we have, and that could be the final plot.
Yeah, that'll be nice if we can get an image consisting of a lot of them combined.
Yeah, I do have the image. I just need to pull out the profile. I do have the average image.
Oh yeah? How does it look?
It doesn't look very different. I mean,
okay.
Because it's all like,
yeah. To mash up.
Yeah, I mean, you see, the only thing is I don't know if you want to present that photo because it can look like patchwork because some things are there for the others and yeah.
Okay.
It can look patchy, so.
Interesting. Yeah, that solution file is huge, right?
This one?
Yeah, so it takes a long time.
I think this must be the one that, no, the previous one was like 170 GB.
Wow.
Yeah, so that's the mesh. And yeah, that's how the profile looks.
Oh.
So this is with, so this is the entire flame profile.
Oh, it's cool.
And then, so this looks very similar to what we saw with the pressure outlet here.
So what we're modeling there is when we have our flame, we have a way to pull sample particles out from, there's a flat plate and there's a hole in that plate where we can pull a sample out of, suck it out, and that's what we're modeling to see how that affects the flow field.
So, yeah.
Interesting.
It's pretty at the least.
Yeah, it has little vortices at the end.
I know. That looks cute.